Example 5. A printed page has a total area of 672 centimeters squared. It is to contain printed material in the center with clear margins of 3 centimeters on each side, 3 centimeters at the top, and 4 centimeters at the bottom. Okay, and that's already been included in the diagram below. Find the dimensions that maximize the printed area. So in other words, find the dimensions that maximize this yellow part in our diagram. Okay, so because that's what we're interested in maximizing, I'm going to declare the length and the width to be the length and the width of this box, or of this yellow area. So there I've declared A, W, and L. So we are trying to maximize the printed area. So we are trying to maximize the equation area equals length times width. So once again, we have one equation with 3 variables. We need to come up with a second equation that allows us to write one variable in terms of the other. So the other piece of information they've given us here is that the total page is going to be 672 centimeters. Okay, so that is our total area. So if we're creating a formula for the total area, it's going to be 672, which is the area, and that's going to equal this length. Okay, and that full length there would be the length of the yellow page, okay, plus the top and the bottom. So plus this 3 centimeters on top and 4 centimeters on the bottom. So length plus 7. Okay. And the width of the full page would be the width of the printed area, so W, plus the 2 extra sides, so plus those 2 3 centimeter sides, so plus 6. So our total area is going to be 672 equals L plus 7 times W plus 6. Okay, and that does give us a second equation that only involves 2 variables. The hard part here is that we have to isolate one of those variables. Okay, so how you choose to do that is up to you. You can expand this out and then isolate from there, or you could try dividing by some stuff to isolate that way. Both ways will work. I'm going to expand it out. So I'm going to choose to isolate the L. So I'm going to move everything else over to the other side. So I'm going to move that 7W over, and I'm going to move that 42 over. So 672 minus 42 would be 630. We move the 7W over, so we get minus 7W, and that would equal LW plus 6L. Okay. To get the L alone, we're going to actually common factor it out. And then we're going to divide both sides by W plus 6, and that's going to isolate the L. So that gives us our second equation, where we've written one variable in terms of the other, and we're now going to sub that in to equation number 1. So I replaced the L in the first equation with 630 minus 7W all over W plus 6. And now before we take the derivative, I am going to multiply in that W. That's just going to make it a little bit easier, so I only have to apply the quotient law. So our area would be 630W minus 7W squared all over W plus 6. Okay. And now you need to find the derivative of that. So take a minute, find the derivative using the quotient law, and then replay the video. So there it is once we've applied the quotient law, right? So we took the derivative of the numerator times the denominator left alone minus the numerator left alone times the derivative of the denominator all over the denominator squared. Our next step is going to be to simplify this if possible. Okay. Or you could set the derivative equal to 0 first and then simplify. So to simplify this, I'm going to expand it all out, which is what I did here. And we can see that there are some terms that cancel. So the 630W cancels with the minus 630W. Okay. And then we can combine those two W squared terms. So that leads us to negative 7W squared minus 84W plus 3,780. And it's all over W plus 6 squared. Okay. So now we're going to set our derivative equal to 0, and we're going to have to solve it. Okay, so remember, when solving a rational equation, the denominator determines restrictions, but it's actually going to be the numerator that's going to give us our solutions. So we can ignore that denominator, okay, but we should also recognize that W cannot equal negative 6, which we already knew because our width can't be negative. 7. There we go. So we are factoring that numerator. So we can start by factoring out a negative 7, which will get us W squared plus 12W minus 540. And that does actually factor fairly nicely into W minus 18 times W plus 30. Okay, and if you couldn't get those factors because they are a bit high, you could always use the quadratic formula to find those two factors. So we get that W equals 18 and W equals negative 30. Okay. So the negative 30, we are going to disregard that because width must be positive. So we only have one solution there, so hopefully it does give us a maximized printed area. So we would want to check this to make sure that it is a maximum. So let's do that first. So using our sign line, if we check on either side of the width of 18, so if we check a width of 17 and a width of 19, and plug that into our area derivative, we do get that it's increasing and then decreasing, so that would mean that there is a maximum. Okay. And if we go back up to the question is asking us to find the dimensions of the printed area, so we need both the length and the width. Okay, so far we've only found the width. So now we're going to have to use that second equation to find the length. So it's the 630 minus 7 times 18 all over 18 plus 6, which would give us a width of 21 meters. So therefore the dimensions that maximize the printed area of the page are 21 centimeters by 18 centimeters. Example 6. Treasure Oak Furniture makes wooden storage chests that have a volume of 0.1 meters cubed. The chests are built so that the width and height are the same. The chests have decorative carvings on the top, which double the material costs for the top compared to the bottom and the sides. Determine the dimensions that will minimize the material costs for making these chests. So I've already started with a diagram here. So it's a rectangular prism because it's a storage chest. And we know that the width and the height are the same. So I've represented the width and the height both with W, because since they are the exact same, they should have the same variable. Okay. And then I've labeled the length of the chest as L. So we're interested in the material costs. So if we're talking about material costs of wood, we're talking about the surface area of it. Okay. So if we think about just the surface area of a rectangular prism regularly, here we would have two of these front and back pieces. Okay, and the area of the front and back is W times W. So I would have two WWs, so two W squareds. Okay, and that is the front / back. Okay, on the side, this would be W times L, and there are two sides. So I have two sides, so 2 L times W, for my sides. Okay. And then because the bottom and the top have different costs, I'm going to keep them separate. So the bottom would be L times W. And the top would also be L times W. Okay, we haven't taken the cost into account at all. So that's the surface area. Now, if we wanted to create a cost formula, something that takes cost into account, the only thing that would actually change here is that we would really consider each of these to sort of have a unit cost of 1. The top, the front, back, and sides all have the same cost. The only thing that's different here is that the top has double the cost. So if everything else had a cost of 1, the top would have a cost of 2. Okay, and I'm using 1 and 2, but for this, you could have actually used, for instance, 100 for everything and then 200 for the top, or 20 for everything and then 40 for the top. It would actually create the exact same answer in the end. But generally, we'll stick with the lowest numbers. If everything's a 1 and something's triple, it would be 1 and 3. Okay, so the cost formula, I'm going to write it out here. It would be just the 2w squared plus 2lw plus 1lw plus 2lw. Okay, and we can simplify because we have a bunch of like terms there. Costs for surface area would be 2w squared plus 5lw. Okay, so there is the equation that we are trying to minimize because we want to minimize that cost. Once again, we have 3 variables, so we need to use the other information in the question to get a second equation. And the information they give us in the question is that the volume of the chest is 0.1 meters cubed. So we can create an equation around volume. So volume is 0.1, and it's going to equal the length times the width times the height. So W squared times L. And using the second equation here, we can isolate for our L. L would be 0.1 over W squared. Okay. And we're now going to use that, and then we're going to sub it in here. So take a minute, sub it in, and then simplify it and take the derivative. Okay, so once we've subbed it in, we can cancel out these w's because there's w on top and there's w squared in the denominator. Okay, and then we have to take the derivative of this. So remember, when we're taking the derivative with the w on the bottom, you want to bring it up and write it as a power of -1, and then take the derivative that way. Okay, so here's our derivative. We are going to set c prime equal to 0, and we're going to solve for w. And the easiest way to do that is going to be to multiply everything by w squared, because that will cancel out the denominator. So we have 4w cubed minus 0.5. And now we want to isolate that w. So we get that w cubed is going to be 1/8. And if we take the cubed root, we get that w equals 1/2. Okay. So we want to do a little verification step now. And so for verifying it, I used a test point of 0 and 1 to check on either side of the half. And I got that c prime was negative and then positive, so that is a minimum, which is what we wanted. So the last thing we have to do is we have to find the length, because that is what the question's asking us for. It was asking us for the dimensions. So to find the length, we go back up to that equation where we isolated L, plug in 0.5, and we get that the length was 0.4 meters. And now we can write out our therefore statement. Therefore, the dimensions that minimize the material costs are 0.4 meters by 0.5 meters by 0.5 meters.